Welcome to Physics 4B. At Foothill College, we're on the quarter system, so this is a 1 quarter long class on electricity and magnetism. It's calculus-based, so it's designed for science and engineering majors. But if you're taking a trig-based class, follow along, skip over the calculus when you get there, and you'll be okay. My name is Frank Coscarano, and I'll be your instructor. Because electronics are so integral in every part of our lives, there are many applications we'll see as we go through this quarter. We'll learn how a photocopy machine works, a lot of simple circuits, metal detectors, how the magnetic stripe on your credit card or driver's license stores information, how speakers work, all kinds of interesting applications, so it should be an interesting quarter. Now, we have roughly 30 lectures, give or take a little bit, to get through our material. And to break up the videos a little bit so they're not too long, I'll make 4 to 6 videos per lecture. So, let's get started. Electricity and magnetism. We'll start with electrostatics. Where does electric charge come from? Well, it comes from the atom. Inside every atom is a nucleus, and that nucleus is made up of protons and neutrons. The neutrons, of course, are neutral. They don't have any electric charge. The protons are electrically charged. They have a positive charge. So we know we have 2 types of charge, and someone had to come up with a name for them, so they came up with positive and negative. One type is positive. That's at the core of the atom, the nucleus of the atom, from the protons. Those have positive charge. The other type of charge, the negative charge, is carried by the electron. The electrons form a cloud around the outside of the atom. Now, most of the time, we have the same number of protons and electrons, the same number of positives and negatives. So most of the time, we're dealing with objects that are electrically neutral. And they don't interact very strongly because of that. But interesting things happen when we can make one of the items charged. How do we do that? By adding or removing electrons. Remember, the positives, the protons, are at the nucleus of the atom. We can't change that. They are tied to the atom. If we took a proton out, it wouldn't be the same atom anymore, right? That's how we define what the atom is. In the periodic table, each atom in the periodic table is defined by the number of protons that make it up. So that's fixed. That never changes. But the electrons can be removed and added fairly easily. That's that cloud around the outside of the atom, the negative charges. If we remove an electron, we remove a negative charge, the same number of positives are still there, but there are fewer negatives, so that means we have a net positive charge left behind. And if we want to make something negatively charged, we add some extra electrons to it. This typically happens when things rub together, when dissimilar materials rub together. Some of the materials hold on to their electrons very tightly, and some materials don't hold on to their electrons very tightly. So when they rub together, the material that holds on to its electrons tighter can steal some electrons from the other material, can grab them and take them from the other material. It will gain electrons and become negatively charged. The other material will lose electrons and become positively charged. How do you know which material gains electrons and which one loses electrons? Well, you can look it up in your chemistry textbook or just look it up online. It's called the triboelectric series. And the triboelectric series lists all different materials and how strongly they hold on to their electrons. So if you have a material up here that holds on to its electrons really strong, and one down here that doesn't hold on to them very strong, and you rub them together, you know this material becomes negatively charged and this one becomes positively charged. But if you take this material and rub it against one that's below it in the triboelectric series, then it would become negatively charged instead of positively charged, and so on. So you can look it up and see which one gains electrons and which one loses electrons. So we know we have two types of electric charge, positive and negative, and it's within the atom itself. The core, the nucleus of the atom, has the positive charges, the protons, and the electron cloud around the outside of the atom, that has the negatives. The electrons carry the negative charge. And we know that objects can become charged when we rub them together, and one object steals the electrons away from the other object. The one that takes the electrons has more negatives than positives, becomes negatively charged. The one that loses its electrons now has more positives than negatives, and it becomes positively charged. Let's take a look at this video demonstration and see how charges interact with each other. Here I'm electrically charging a balloon by rubbing it with a piece of wool. Now I'm going to rub a PVC pipe with the same piece of wool. Both of these objects, the PVC pipe and the balloon, have the same sign charge. In this case, both are negatively charged. What can we say about like charges? Gravity wanted to pull that balloon to the ground, but the electric interaction, the force between the balloon and the rod, counteracted gravity, and the balloon sort of hovered there. So that means that like charges, because we know the balloon and the rod had the same type of charge, they're both made from the same type of material, and they both were rubbed against the same piece of wool, so they both had the same type of charge, and that repelled each other. Like charges repel. If we have two positive charges, they will push apart or repel each other. Or if we have two negative charges, because we have two different types of charge now, positive and negative. Either way, the force is repulsive, as long as those charges have the same sign. Now let's watch a video demonstration between oppositely charged objects and between a charged object and a neutral object. Don't forget to pause the video and make a prediction. Try to explain it. You'll get a lot more out of the videos and a lot more out of the lectures. This is an ordinary balloon. What's going to happen after I rub it against my hair? Now I'm going to take that balloon and hold it up to the wall. That wall is an electrical insulator. Stop the video and predict what's going to happen when I let go. As you probably knew, the balloon sticks to the wall. Now I'm going to take the balloon and hold it up to this aluminum pie plate. That's an electrical conductor. Pause the video and predict what's going to happen when I let go of that balloon. That electrically charged balloon is attracted to the conductive pie plate. It was also attracted to the insulating wall. The charged balloon is attracted to the conductor and the insulator. The first thing we saw is that opposite charges attract. When I rub the balloon against my hair, one object becomes negatively charged, one becomes positively charged, and they attract. With those opposite charges, they exert forces on each other that are toward the other charge. So the positive charge feels a force pulling it toward the negative charge, and the negative charge feels an equal and opposite force pulling it back toward the positive charge. The second thing we saw was that a charged object can be attracted to a neutral object like the wall. let's take a look at what's going on there. When we hold up a balloon next to the wall, there's my wall, there's my balloon, and I'm not a very good artist, so maybe I should label this so you know what it is. That's a balloon, or my rendition of a balloon. Let's make our balloon negatively charged. So there's some excess negative charges on that balloon. We bring it up next to the wall. The wall is an electrical insulator. That means that the electrons are tied to the atom that they surround. They cannot move around within the material. They're tied to a specific atom. But the electron cloud around that atom can shift a little bit one way or the other. Even though those electrons can't move and go somewhere else in the material, the electron cloud can shift a little bit one way or the other, making the atom polar, giving one side more positive charge and one side more negative charge. And that's what happens when we bring that balloon up to the wall. If the balloon has excess negative charge, the electron cloud in each atom that makes up the wall gets repelled. And the atom, if we zoom in on it, sort of will look like that. The electron cloud gets pushed back a little bit, so one side will have more positive charge, one side will have more negative charge. And if we keep drawing more atoms here, of course I'm zoomed in very, very close for looking at individual atoms, but you get the idea. They would look something like this. Now, what we see here, this wall is a non-conductor. What we see is that the very surface becomes positively charged, and all of this stuff back here sort of ends up canceling out. It's basically neutral back in there. But that slight positive charge at the surface interacts with the negatively charged balloon, opposites attract, and we get an attractive force. Now, were you able to predict what would happen with the conductive pie plate? Did you think the balloon would stick to the conductive pie plate? It works out in a very similar way. When we bring that charged balloon up to that conductive pie plate, what's the definition of a conductor? The electrons are free to move throughout the material. They are not tied to each atom like they are in an insulator. They can move throughout the material freely. So when we bring that negative charge up, there's an electron over here, and that electron decides it wants to get as far away from that negative balloon as it can, so it moves off somewhere on the other side of the pie plate, leaving a positive charge behind. And another electron moves off somewhere to the other side of the pie plate, leaving a positive charge behind. And another electron moves off somewhere, leaving a positive charge behind. So you're left with some positive charge here on this side of the pie plate, and on the other side of the pie plate you get some excess negative charge. But in electricity, closeness counts, and the positive charge will exert a greater force on the negative balloon than the negative charges, because the negative charges are farther away, and we get an attractive force. So it's possible to get a force between a neutral object and a charged object, but it can only be attractive. We can never get a repulsive force because of this phenomenon. So if we get two objects, if we know two objects attract each other because of an electrical interaction, we know at least one of them is charged. The other one might have an opposite charge, or it might be neutral. We don't know. We would need more information. But if we are told that two objects repel each other electrically, They have to have the same charge. Both objects have to be charged with the same sign charge. Let's see if you've got it by watching this next demonstration. What's going to happen when I hold up this electrically charged PVC rod next to this neutral aluminum can? The can and the rod attract each other. The aluminum can is a conductor, but it's electrically neutral. Only the PVC rod is charged. You can use any charged object. After rubbing this balloon against my hair, it charged up and it acts just like the PVC rod. This is exactly what we've been talking about so far. Our rod was charged. Let's make it negatively charged. Our aluminum can was electrically neutral, but you bring that negative charge up next to it and the electrons are free to move throughout the aluminum can. Where do they want to go? As far away from the negatively charged rod as they can get. So they gather along the back side, on the far side of the aluminum can. That leaves some positive charges on the other side. And the charges that are closest exert a larger force. So the interaction between the negatively charged rod and the positive side of the aluminum can is a stronger force than the negative side of the aluminum can with the negatively charged rod. And that means you get an attractive force. So we've got a neutral can, a charged rod, we get an attractive force because of this induced charge separation in the can. Let's take a look at another video demonstration. The small pieces of paper are electrically neutral. The PVC rod is negatively charged after rubbing it with the wool. What's going to happen to those pieces of paper? Pause the video and make a prediction. The small pieces of paper are attracted to the rod. But let's watch again in slow motion to see what happens after they touch the rod. After touching, they repel each other. So we're looking again at an interaction between a charged object and an electrically neutral object, the pieces of paper. And they are electrical insulators, kind of like the wall we looked at earlier with the balloon and the wall. And up here I made the balloon negatively charged and showed that it would be attracted to the wall. So let's make our rod positively charged down here. It doesn't matter what charge the object is, it's always attracted to a neutral object because of this mechanism. So if we made our rod positively charged, and like I said, it doesn't matter, positive, negative, we're going to get an attractive force either way. The electron cloud shifts a little bit. The electrons can't move. The paper is an electrical insulator, but the cloud can shift a little bit, leaving a slight negative charge at the surface. Because the electrons are attracted to that positive rod, closeness counts in electricity, and we get an attractive force. But what happens when the paper touches the rod? When they touch, an electron can jump from one to the other. So the electrons are attracted to that positive rod. Where they touch, the electrons can jump across, and maybe an electron will go up here. And what's that going to do? It's going to leave some positives behind. Now we have like charges, and they will repel. So the paper will fly off after it touches the rod. At first, there's a charge induced charge at the surface due to the electron cloud shifting a little bit, even though the paper is still electrically neutral. We get an attractive force, but when they touch, an electron can jump across. And now we have like charges, and usually the net charge overrides the separation that occurs from the cloud shifting a little bit, and that's what dominates. And so once you get like charges, you get repulsive force between those two objects. Before we stop this video, let's take a look at some of the areas where we see this all the time. When do charges transfer? When things rub together. Where do they rub together? In your dryer, right? You've got socks and other things in there tumbling around, and they rub together, and it's a nice dry environment, and some objects become negatively charged and some become positively charged, and you pull your shirt out and there's a sock stuck to it. So the electric force can be quite strong, right? It can hold up the weight of the object. See that there. Sometimes you pull a sweater off over your head on a dry day in the wintertime, and you get some static cling. Your hair will stand up a little bit. Maybe you've seen a kid going down a slide, a plastic slide at the park, and their hair gets kind of stands up a little bit, or they come over and touch you and they get a shock. It's all the same phenomenon. And even the plastic wrap we use to seal up our dishes and save our leftovers in the kitchen oftentimes it sticks because of electric cling, static cling. When the plastic wrap is peeled off, charges get transferred and it sticks electrically to the dish.